Hey kids, welcome to another lesson on discrete math, this one on the binomial theorem. Now we did a little bit of this without calling it the binomial theorem in AAF or in Algebra 2. But don't really expect you to remember it. So that's just as if we were starting from scratch. Binomial, remember a binomial is two terms, a group of two terms. I want you to expand this binomial when I put an exponent on here. And I want you to find, I might ask you to expand it all, or I might ask you just to find me the fifth term in that expansion. So a little bit of an algebra review. Remember that a plus b squared does not equal a squared plus b squared, right? That only works if n is 0 or 1. So another way for me to write what list I want you to use for n is an element of the discrete set, which means there's nothing between 0 and 1. Okay, so that's what I want you to use. And I want you to expand this. Well, that would be annoying for a plus b to the fifth, so I'm going to do it for you. A plus b to the 0 is no big deal, right? Because anything to the 0 power, except for 0, is 1. Anything to the first power is itself, but a plus b squared has 3 terms. A plus b cubed has 4. A plus b to the fourth has 5, and a plus b to the fifth has 6 terms. This is beautifully symmetric, right? Notice the coefficients all here on the outside. Look at that triangle. Isn't that beautiful? Also notice the symmetry, the vertical symmetry. Right? 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 4, 4, 1, 1, 5, 10, 10, 5, 1. That kind of looks familiar. There's an incredible amount of patterns inside this pretty simple concept of just a binomial expansion and just keep increasing your powers of n. I am sure many of you have heard of this before, called Pascal's triangle, over the famous mathematician, really philosopher. That's what before they came up with the name mathematician, philosopher Blaise Pascal. He's from France. Firstly, his first name is awesome, Blaise. That is a great first name. Also, he made many, many contributions to mathematics and philosophy. Look up Pascal's sayings, right? A lot of inspirational sayings like this, right? Don't try to add more years to your life. Better add more life to your years. I mean, that's a powerful thing to think about. Also, he was a very passionate man. I mean, he was from France. That's pretty stereotypical, right? And he fell in love, and there was some issue. I don't remember. I'd have to go back to the history, which I do love. But he fell in love, and there was some issue. He had to have a duel over this woman, and he was fairly young. I want to say he's like in his mid-20s. And he died in this duel. And the woman was so heartbroken, she went away and to a convent and never, married or came out of the convent for the rest of her life. Pretty amazing, right? Kind of cool story. Real people. It's hard to imagine. It's not just a story. It's real people. Okay. Anyway, patterns. There's a product of AB in every term of Pascal's triangle. And you're going to be like, wait, Ms. Getzel, what you talking about? Oh, don't want the highlighter to be blue. The product AB is in every term. Well, you certainly see an A and a B here. You just see 4 A's, right? A times A times A times A, but the product of AB is there, right? Just with different exponents. So even though you don't think there's a B here, there is. You don't think there's an A here, there is. Every time you don't see an A or a B, there's an A to the 0 or a B to the 0. These aren't zeros, they are squares for different exponents. I've already went through this. Every row of Pascal's triangle has the n, the exponent that you're raising the binomial to, plus 1 terms. The power on A always starts at n, right? So for example, where n is equal to 3, the power in the first term of A starts with 3 and then decreases to 0. The powers of B start off at 0 and increase to 1. I'm sorry, increase to N, right? So we actually dealt with those patterns last year. But right, I taught you a different, way of coming up with these coefficients that you can go back in your notes or little book and look up. But now I'm going to give you a shortcut to finding those coefficients. And I hope you won't be surprised to find it has to do with our prior discrete math topics. So I want you to think about here in this row, a plus b to the fifth. This is a product of 5 binomials, a plus b times a plus b times a plus b times a times b, and I ended up with 1, 2, 3, 4, 5, 6 terms. From that product, how many terms have 0 b's in them? Only 1, right? So, and look at the coefficient. The coefficient is 1. So on b, here's its exponent. How many different exponents could I have? The highest exponent is 5, right? 5, 4, 3, 2, 1, and 0. So of the exponents on b, how many choices did I have? 5 choices. And what did I choose? 0. 5 choose 0. What's 5 choose 0? Well, that's 5 factorial over 0 factorial times 5 minus 0, all factorial, which is 1. What? Let's look at the next one. How many terms have only 1 power of b? So of the 5 powers, of the 5 powers, I chose 1. What's 5 choose 1? 5. Oh, my Lanta. How about this? Looking just at b, there were 5 powers to choose from, 2 slots, right? Because that's really b times b. 2 powers of b, or 2 products of b. Oh my gosh. Combinations. The coefficients of Pascal's triangle come from combinations. Coefficients, combinations. And you might be saying, well, how come you didn't do A, Miss Getz? Talk to me. That would be the same, wouldn't it? Wouldn't it be the same? If I did A, I would say, how many choices of powers did I have on A? And how many did I end up? How many powers? I had an A times A times A times A times A. I had 5 of them, 5 A's out of the 5 possible powers on A, right? Crazy. But isn't 5 choose 5 the same as 5 choose 0? Didn't we figure this out before, right? The beautiful symmetry with combinations and the symmetry in Pascal's triangle. Why is the binomial theorem written in terms of these B powers? I don't know. Go ask Blaze. Oh, can't. He's super dead. So the binomial theorem for all n, where n is an element of a positive integer, the binomial expansion has n plus 1 terms, where the power on A starts at n and ends at 0. And the power on B starts at 0 and increases to n. And the coefficients come from our combinations formula, which also come from Pascal's triangle. Whoa. Whoa. Thanks, Blaze. So, can you give me the next line in Pascal's triangle? Now, getting the next line, I can kind of recursively do that, but I want to actually use the binomial theorem. So what do I have? To use the binomial theorem, n is equal to 6. Therefore, there are n plus 1 terms. N plus 1 blanks. 1, 2, 3, 4, 5, 6, 7 blanks. Let's put A on every blank and B on every blank. But the powers of A start with n. Put B on every blank. But the powers start with 0 and end with n. And then the coefficients come from Pascal's triangle, which comes from combinations. 6 choose 0, 6 choose 1. And you hopefully, whoops, didn't mean to make that a fraction. Hopefully you can see the symmetry here. You know what's going to repeat. Now, if you have your calculator, you want to go ahead and get it out for me. Well, for you, and I'm going to show you something that you can spit these out very quickly. And of course, you can look it up, and there's computer programs. But if you have a calculator, we want to do 6 choose 0, 1, 2, 3, 4, 5, and 6, right? That's what we want to do. So on your calculator, on your home screen, type 6. Do your math, arrow over to probability, and choice, what is it, 3 or 4? I always forget. I have to always go look. Choice 3. Enter. But then don't enter one number. Find the squiggly brackets on your calculator. That is above 8. Above 8 is your open parentheses, but if you hit second open parentheses, you get the squiggle. Second parentheses gives you the squiggle. Now type in 0, 1, 2, 3, 4, 5, 6. Your comma is above 7, by the way. Close the squiggles. That is second close parentheses. And hit enter. And look what you get. Whoa! Crazy, right? You get all the coefficients. And your coefficients are 1, which I didn't really need my list for, right? 1a to the 6th plus 6, a to the 5th, b to the 1st. And then it's going to go back down. Right? When you have 7 terms, right? You're going to have 1, 6, 15, and then 15, 6, 1. When you have an even number of terms, they're going to, right, you won't have that single middle term. Pretty cool. Let's do another one. This one, be careful. Still gonna use Blaze. I don't really need my combinations. I already know what my power of 5, those coefficients are, right? Just look at your previous, right? Our slide in your notes. 1, 5, 10. Then I'm going to repeat back down because I have an even number, 10, 5, and 1. But don't forget, this is like your A now, so be careful. Right? Keep organized. I am going to have power of 5, 4, 3, 2, 1, and 0. 0, 1, 2, 3, 4, and 5. But be careful, your A is 3p squared. Now, nicely, your B is just a 1. And then when you have a negative in here, your signs are going to alternate, as opposed to when you have a plus, they're all positive. When you have a negative, so positive, negative, positive, negative, positive, negative. Now, I would expect you to clean that up, right? 3 to the 5th is 243. P squared to the 5th is p to the 10th. 3 to the 4th is 81. 81 times 5. Yes, without a calculator. Yes, without a calculator. It is nice because I just have one, right? It's all just times 1. Okay? Blah, 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 blah. Now, here is that other part of the objective where I don't want you to do a full expansion, right? I'm not asking you to do a full expansion. I just want a term in the expansion. So your job is to figure out which one of the blanks looks like that, right? Well, think about your formula, right? What did my choose formula, what did it come from? Think about your B, which is Y in this case. I have 15 choices. And how many do I want on my B term? Right, so 15, choose 3. Just do that on your calculator. Look at this one. So I'm actually just going to take this part and to just blaze that part first. So a plus 2 to the 4th, 1, 2, 3, 4, 5, right? I have an A times a 2 on each blank. Everybody's positive. And my Pascal's triangle row, or I can just do my combinations formula, right? I will get that 1, 1, 4, 6, 4, 1. And then my powers. Start with a power of 4. So 4 times 2 is 8. 6 times 4 is 24. 4 times 8 is 32. And 2 to the 4th is 16. But I'm not done, am I? What do I need to do? Yes. I need to multiply by a plus 1, which is just freaking algebra 1, right? Clean all that up. Oops. It's a 16, by the way. Woohoo! All right. Done and done. Good job. I will see you in our next live session.